Hello everybody. Good morning, good afternoon, good evening, depends on where you are. Welcome to one more telecom seminar, which is hosted by the Technology Innovation Institute in Abu Dhabi. I'm Dr. Daniel da Costa, currently a principal researcher at the Technology Innovation Institute. And we are running a series of telecom seminars along the last months. And for today, we are pleased to welcome Professor John Cioffi from Stanford University, as the speaker of the seminar. So Professor John Cioffi is currently a life fellow of AIDRC, and he received the bachelor degree in electrical engineering from the University of Illinois at the Urban Campaign in 1978, and the PhD degree in electrical engineering from Stanford University in 1984. He was with Bell Labs from 1978 to 1984. And he was at IBM researcher from 1984 to 1986. He is the founder of Amati Communications Corporation in 1991, and he is the chairman and the CEO of Asia Corporation. He has been a professor of electrical engineering at Stanford University since 1986. Now he's called emeritus. He has published more than 800 papers and more than 150 licensed patents. His research interest in the area of high-performance digital transmission. He's a member of Internet since 2014, the Consumer Electronic Hall of Fame since 2018, the US National Academy of Engineering since 2001, and the UK Royal Academy of Engineering since 2009. He is also a Marconi Fellow since 2006. He received the IEEE Alexander Graham Bell Medal in 2010, the Kirchmeier Medal in 2014, and the Millennium Medal in 2000. He has served over a dozen boards of directors. Currently, he serves as the chairman of the board of Fine Tunes and the vice chairman of the board of the Marconi Society Antenna Corporation. Actually, Professor John Cioffi would need no introduction. He is a very renowned professor of our community. He is the inventor of symmetric digital subscribed line, ADCL, and currently he is also in the advisory board of TII. So in this talk today, he will discuss a very interesting topic, which means translink convergence. And from what I understood, is a path to achieve the most aggressive goals of 6G. So, Professor John Cioffi, thank you so much for accepting our invitation. I know the time is not too convenient for you, so thank you for your understanding and for your availability to deliver this talk. And now the floor is yours.
Well, thank you very much, Daniel, for your very kind introduction, and thank you to everyone who's out there virtually or understanding the time differences across the multiple continents here. Some of you may be watching this on a tape delay, but thank you for the opportunity. Speaking in a few capacities here today, companies, the TII Advisory Board, which I just recently joined, and recalled Professor Emeritus, recalled meaning back teaching again, basically at Stanford University. The subject, translink convergence, is, as you'll see, I'll describe why I chose those names for this particular topic. It's a mix of some things that are really kind of futuristic telecommunications research, but also some things that are pertinent even in 4G and 5G cellular communication and Wi-Fi as well. But it's a provocative subject, and hopefully I'll get everyone to think a little bit with some of the ideas here with translink convergence today. So let's look at the traditional triangles, which I've oversimplified here a little bit. I think many of you have probably seen the 5G triangle, which had basically 10 megabits per second per meter squared as kind of an objective for the speed of transmission in wireless and 5G. Latency was 1 millisecond, and then the massive machine type communications, a lot of devices in a small area, one device per meter squared. What happens with 6G, with the larger circle and the larger triangle you see, is basically everything's increasing roughly in order of magnitude. The data rates, the peak data rates, are actually going up by more than an order of magnitude. And so this creates a number of challenges for the cellular industry. So when we look at this as researchers and trying to do our best to help and meet those goals, how can we get there? So this talk will try to describe that. I might add also that the speed per device is actually not 10x, but actually trying to get 100 times more with these 6G goals. They'd like it to be sustainable, much more power efficient, order of magnitude there, lower cost. Cost is probably the biggest limiter to wide deployment of 5G and Open RAN concepts today, simply because it requires a lot of infrastructure build to get closer and closer to customers to use the higher frequencies and the capabilities of 5G, and more secure, and then just a better link budget, better performance. So that's a pretty tall order, a lot of things there to try to improve as we go to next generation of cellular communications, or more generally to wireless, including Wi-Fi, when I say that. So let's look at some of the salient features of wireless today. If we were to look at the smartphone data traffic, 80% of it is actually indoor, okay? And some go as far to say 80% of all the internet traffic in the world flows on indoor or Wi-Fi signals today. Now that's changing a little bit, the cellular portion increasing, but what happens is the 5G network uses multiple antennas, MIMO, to try to improve the capacity, get higher signal bandwidths focused in specific directions to different users, but it has a difficulty when it tries to go inside buildings. We're going to talk a little bit more about what that difficulty is, but suffice it to say for now that there's a very weak signal that enters into the buildings. And so that's a limiter on 5G as well. We have all these goals, but we also have that problem to consider. Now, you can use mesh systems. Wi-Fi is an example of mesh systems to try to extend indoor coverage by basically relaying the wireless signals from one device to another. But that often has great difficulties because of the roaming among the multiple routers. Most of the commercial mesh Wi-Fi systems today, for example, actually perform more poorly than the systems that are not using the mesh. So there are some issues with that. Reuse of the same spectrum is not possible, so they have to share the spectrum, and then getting the various devices to latch onto the proper signal is challenging indoors. So all of these things create some issues for wireless transmission and leave us with a situation where the coverage or the accessibility of wireless is not as good indoors, even though that's where most of us are using the wireless signals. So the big question here at the bottom, there often exist wires. So can they easily assist wireless? Can they help us meet those goals? And so that's what TransLink convergence is going to try to attempt to address. Look at that, getting the signal indoor and trying to meet these objectives that we see. I'm just going to check the chat box because I'm seeing 5 questions there as I'm speaking. Those look like just logistical questions, so no on the features. So let's go back to cellular signals and the path to the end device indoors, if you will. We have a cell tower over here on the left, and let's say this signal is 100% power, obviously coming out of the tower. That's the source power, but it undergoes the environment, and maybe it loses half the signal strength. as it passes through the environment, whether it's the atmosphere or leaves or foliage that causes that. And then it may have to go through other buildings or around buildings that are in the path or other obstacles that can further attenuate signals. It has to go through the walls into the home. Depending on what the walls are, they may diminish the signal significantly. And then finally, what may happen is a much smaller signal actually makes it to the end device, hopefully enough to communicate well, but often not good enough to do that. And indeed, there is a further issue when we start to look at the generations of wireless transmission going back to 3G. Well, they use lower frequencies for 3G. And as most of you probably know, the propagation capability as we go to higher and higher frequencies is not as good. They don't propagate as far at higher frequencies. So as we go to the higher frequencies and higher bandwidths of Wi-Fi or LTE 4G, there's a greater loss. And as we go to 5G signals and bandwidths, yet even greater loss due to all of these things because they're using or occupying higher frequencies in the spectrum. One of the issues is going through walls is just difficult. If you look at a signal going through a wall into a building, or maybe trying to pass through a few walls, maybe come out the other side, go to a device. If we were to look at just the basic signal loss, many of you may understand this. And of course, if we look at a spherical surface, and we know that the surface area is proportional to the square of the radius, so there's a loss that way. But there's also, and that's kind of a perfect free space loss. We can see also a loss due to just as the frequency goes up, the attenuation increases as the square in kind of a good environment, even and with or without a MIMO, you see these effects. What the MIMO tries to do with multiple antennas is focus that energy, reduce that loss, but the higher frequencies, even if you have MIMO, do create some limitations. So here's a simple model. I don't have too many equations in this talk, but there's some nominal loss in the channel for transmission. And then there's a distance loss. The further we go away, this is kind of like the spherical loss I was talking about, but sometimes it's not just proportional to the distance squared, like the surface area of a sphere. We have an attenuation coefficient that typically is somewhere between 1.5 and 4.5. Usually it's in that 3 or 4 type range for most practical transmission systems. So there's a substantial loss from that. And then going through walls, this is an oversimplified model, but one of the models that you will see and use is you lose about 18 dB, so almost a factor of 100 in signal power for every wall that you pass through with a wireless signal. And that's a substantial loss, of course. So the result is, of course, weak signals. And that effect is more pronounced as we use higher and higher carrier frequencies in wireless transmission. Okay, so I'm talking at a high level in terms of the concepts. If you want to see more in detail, this paper, which was an invited paper 3 years ago, the IEEE Transactions on Communication, called Cellular Subscriber Lines, talks about this particular topic of trying to combine the wireless and the wireline together. I'm not talking about a femtocell or a router that digitally repeats signals. I'm talking about the analog signals themselves. And so you can see in this depiction here that 100% wireless signal has a baseband equivalent. If you're taking basic communications classes, you're familiar with that, the so-called baseband equivalent. The latest wireless standards have something called the X-Hall split 7.2, which is basically this baseband signal. You can think of it as the samples of the in-phase and the quadrature signals that are sent, for instance, in a QAM modulation that's used heavily in wireless systems. And those signals are available. And the idea is to use a tuner, if you will, basically a carrier a multiplication that basically takes that signal to an intermediate frequency, IF, and it passes, okay, as basically an analog signal at a good bandwidth on the wireline transmission system, maybe a few hundred meters. And then perhaps it's inside the building or inside the home. It goes wireless, okay, at a different carrier frequency. But if these systems are properly synchronized on the different tuners, then basically the entire path looks like the cascade of the transmission path of the wireline channel with the wireless channel, even though there are different frequency bands. If these two frequencies are locked, they don't have to be the same frequency, they just have to be a certain rational fraction multiple of one another, which is easily done in today's systems. Then basically that becomes a single translink, if you will, channel. Translink meaning wireline and wireless. That's why I call it translink. And of course, we talk about convergence of fixed line and wireless networks. So translink convergence, hopefully that name makes more sense to you now. It's across the links. Now, what can happen when we do this is there's orders of magnitude less power necessary because this transmitter over here on the right at the radio frequency unit, when it gets converted there, is very close to the devices inside the home or inside the building. And so you don't need a lot of power to transmit to make that particular connection. If you're trying to transmit someplace further back with an antenna, of course, you need more power. So you can get up to 10 times better rate or coverage than wireless alone, simply because you have less attenuation along that path. And the cost, if we just have tuner circuits here, I'm going to talk more about the cost of tuner circuits shortly. That's an order of magnitude less costly than what you would see if you had a full router or a femtocell or another type of device that was doing digital to analog and analog to digital back type conversions and having the full femtocell functionality, let's say in the home attached there. So it's not a femtocell that we're looking at. It's not quite radio frequency over fiber either, because we're using these tuners to move the frequencies around. So there's a little bit of complexity there. And I'm going to argue that that's a pretty good combination here as we proceed through our presentation. So let's look at that from a block diagram standpoint. We have a cellular base station over here on the left, and it's using what's called X-Hall split 7.2. That means you get the in-phase and quadrature samples directly from the interface. That's an interface that's well-defined in the ORAN, Open RAN, standards activities for wireless. Those signals downlink go across a transmission facility. I'm calling it link 1 here. There's a certain transfer function. The uplink direction is also a transfer function. Then they go through a second link. It might be a different one, might be a fiber, one might be a copper. They both be fiber. And then finally, in the last link here, they're going wireless. That's the part that I showed earlier that's inside the home. And what happens is basic system theory and communications, the transfer function across this cascade of links should be basically the multiplication of the transfer functions. So the question is, what goes in those places in between? Well, these are the tuner circuits. But a tuner by itself is not quite enough because we have to multiplex both the downlink and the uplink signals, perhaps on a single wireline connection to do that. And so what we're going to do is actually do some tricks with signal processing, where we're going to burst those samples across. We're going to increase the sampling rate of the samples. It's not going to be a digital signal. It's going to be a discrete time signal, where we're going to change that clock rate, if you will. And in doing that, we're going to have to capture the samples and maybe buffer them so that we can create bursts, so forth. So we'll need a little bit of memory, some small processing capability, and of course, conversion devices like digital analog converters and analog to digital converters. So then each link is an intermediate frequency system with what I call frequency scaling. That's basically the bursts that we're talking about. Now, I'm going to talk a little bit about bursts and what that does to the transfer function shortly. So think the ORAN split 7.2, the in-phase and quadrature samples, and each is enduring or traversing, should be not transversing, a link, and we may have a cascade of those, and so we have translink convergence. Now, it's not just a theoretical concept. There are some companies trying to do this. Here's one of them. PhiTunes is the name. There's a website you can go to and get a little more information there. And as I mentioned, there's this paper that was published a couple of years ago on this particular concept. And so the question you might have is, well, does this work? Or can the 5G or even 4G transceivers, certainly 6G transceivers, considering the future, can it handle that cascade of distortion across that all those links? And it can. And that's because the 5G transceivers that are in use are pretty good. They tend to operate at a pretty high performance level. And to them, this cascade just looks like another wireless channel. The copper limit, of course, copper is not as good as fiber for transporting the signals on this. But nonetheless, if you look at this, I'm going to show you some graphs later that give you some measurements on how far you can go with the 5G signals on copper channels. It's about 1 kilometer or so for the types of data rates that we see in 4G and 5G today. Depends on the exact situation. It does require timing, accurate synchronization of all the systems. If you're familiar with the IEEE 1588 timing standard, which is basically something that's used network-wide to try to make sure that all of the base stations out there are all kind of sending downlink and uplink in a synchronized fashion. But that's already there. And that would need to be used in this translink convergence as well. So I am arguing that this particular type of system is a path that helps get to these order of magnitude improvement goals that we started the talk with. So let me talk more about this frequency scaling or burst transmission. Let's just look at a simple wireless system. I've shown some samples there in the time domain, and then the lower graph is the frequency domain. The signal is being sampled, it's being maybe converted to analog, it's transmitted maybe at a certain carrier frequency. Think of that as these samples here. And it might have a spectrum in the frequency domain that looks like this hump here, maybe centered around a carrier frequency. If I push those same samples closer together, what happens is the signal energy in the frequency domain kind of spreads out a little bit. It expands, and that's what I'm calling frequency scaling. And if I push them even closer together, burst them even more quickly, then the energy is spread even over a wider range of frequencies. But I can do that. It's the same samples, basically, that are happening. It's just how fast do I clock them into a channel or into a digital analog converter, if you will. But the links transfer remains linear. Okay, it may be a scaled or frequency scaled linear transformation, but you can multiply the different transfer functions as long as you take care of the frequency scaling. In doing that, you will have a linear channel, and that's what you need for the various cellular techniques, 5G, 4G, and elsewhere to otherwise to work. Now, one of the interesting aspects of this split 7.2 that I keep referring to is that presently today, there are functions in what are called the Open RAN radio unit, if you will, ORU, that you can think of that as basically very close to the antenna. Okay, so that's the signal processing in the dark blue color that goes there. And then they have other functions that are more distributed. They're back at the mobile edge. Those are the green functions. most of us in transmission in the past tend to think of all of these functions being located very close to the antenna, or the antenna driver circuits, if you will. And that's being split, and the green functions are being shared in a computing facility. You see things like equalizers, decoders, and so forth. They're occurring at the mobile edge. They're not out at the radio edge any longer. Now, the current specification actually is this red curve that you see here. There are certain functions that are left out at the radio head. They do have the beamforming processing there, a few other things, but a lot of the processing remains at the mobile edge. Now, one of the things that happens is the calculation of the beamforming coefficients for the antennas. This is how they shape the gain and the phase of the signals that are going into the antennas for the MIMO system. They need to be computed somewhere. And that calculation presently they thought it should be over here in the green portion, so you can see the red curve here. What happens is when they get the results of that calculation and they try to get the beamforming coefficients to the right places for a reasonable 10 gigabit per second or 10 reasonable transmission system, reasonable cell today, it actually takes, which is got 10 gigabits per second of wireless information being transmitted. It actually takes 17 gigabits of overhead just to get those beamforming coefficients out there. The total overhead is about 27 gigabits per second. Presumably they have a fiber, so they have that bandwidth. So there's more bandwidth on the fiber than there is in the wireless signals that are being transmitted. But the 17 gigabits per second just to handle these functions is a lot to do that. And so the idea is, well, maybe we should move those functions, put this new interface here that Ericsson has proposed, and put that beamforming calculation back at the radio edge. Of course, that moves cost and power and makes the radio edge more expensive to do, which is not necessarily good for the adoptability of the wireless systems. Okay, so if we go back to the concept of the translink convergence, what might that look like for a system? Well, at the DU, okay, where this mobile edge computing is going on, there may be some kind of device here shown by this box. There might be a short copper connection here and maybe a longer connection out to the home or the enterprise and so forth. And the wireless baseband 7.2 signals basically are those samples, and they're going to propagate out to the different endpoints and then go wireless inside those endpoints. Now that is a tuner circuit at these different points that we're talking about, which is a lot cheaper than trying to put cellular processing or move all of that functionality back out to these antenna sites. We'd like to keep it at the mobile edge. And what this also does is, of course, because the signal is riding on wires further out, and it's a lower power signal, there's a lot more capability to reuse spectrum if we're leveraging any wired infrastructure that's presently there. So it's eco-friendly, uses less power, and of course is a better preserver of spectrum. We can take this inside the home and use it on Wi-Fi as well, as long as you have some kind of cabling inside the home. You can use the same IEF concept, take the Wi-Fi baseband signal, the equivalent of that 7.2 split in cellular. There are equivalents in Wi-Fi, and you can run on wires inside the home. And in this case, you don't need the mesh network in the home, or you don't need a wireless mesh network in the home. You don't even need a mesh network in the home because these are tuner circuits. So again, the same concept being used there. So it's essentially a single frequency Wi-Fi home network, and it makes efficient use of the unlicensed bands for that. And very controllable roaming on the system, because your processing, your Wi-Fi access point can handle all of that and doesn't need to coordinate with a bunch of mesh points throughout the building. as long as you have a wire, you can do this. So that kind of is the basic concept of translink convergence. What I'm going to try to do here, and hopefully not get too overwhelming with it, is just provide a little bit more detail. If you've stayed with me to this point and understand it, you may have some questions that are floating around your mind exactly how you would do this. So we'll try to address that here. So if we look at a simple system design, we have this, and here I'm looking at cellular. So we have this radio access node baseband split 7.2, the I and Q samples. They go into, I called it a 5G, let's think of it that way, intermittent frequency modulator. This will put it at frequencies that will pass on a transmission line. Here I've shown a twisted pair that could be a fiber or a coax as well. It rides on that in one direction. There's the burst downstream, and then you have the burst upstream. So you keep basically doing ping pong or time division multiplexing here to go back and forth across that wireline infrastructure. You slow down the bursts to the rate they need to be for the wireless system. You put the proper carrier frequency on it, and you send it to the antenna. It goes out to the device, and similarly coming back, we do that. We down convert, if you will, to the IF frequency, burst across, and then come back to the split. So that's a basic idea. If there's not a direct connection to a distributed unit for the wireless system, then you can optionally modulate this to wireless and then demodulate it again at a point where you have the wires that go to the homes or businesses that are being connected. So the mobile edge physical layer computing is going to see an equivalent channel. It's going to include those stretched or frequency scaled wireline channels as well as the wireless channels. So if we look at it, we might have the IQ spectrum looking as a baseband signal like this coming from the split 7.2. We're going to upsample it. That's what this arrow means here, increase the sampling rate. So we're going to spread it out. And it goes through a wireline channel. If it's a copper wireline channel, it's probably going to be somewhat low pass. They won't pass DC, but that's not too important. But it will attenuate the higher frequencies. So you will distort the signal a little bit, and you're going to do it over that wider bandwidth. And it's like a transfer function that's multiplied there. Then we'll reach the point where we want to go back to wireless. We'll slow down the sampling rate to the original sample rate that we had over here. That signal will be now shaped, and this shaping, this distortion will be included. And then, of course, that will go through some kind of wireless channel, which may add additional scaling and distortion to it. And we get the cascade or the translink transfer function, if you will. And the existing wireless system handles this as if it were a wireless channel. Now, here is actually kind of a system diagram from that paper I mentioned earlier that gives you a little bit more detailed kind of concept here, but you can see certain things happening. If you're familiar with the 3GPP standards, there's a 1.92 megahertz signal that's very commonly used to create all of the signals. There's an integer m that can multiply that, and the m can be 1248. As you can see there, any of those values, the really wide bandwidth systems have a higher m in them. You take the signal, the baseband signal, and essentially gather it into a buffer, if you will, and then you're going to create those faster samples, and then you're going to send them through a digital analog converter and your line driver and onto your wireline connection, and do the same thing in the reverse direction. And so you're going to be separating the two bursts. In there, you can see some extra functionality here. And what that is a control channel, very low rate control channel. So let's say we have a carrier frequency here. This is the wireless signal that's been frequency scaled. In this case, we're showing it going up by a factor of 8/3 with respect to its original bandwidth. We sneak in a down control channel, an up control channel. Nominally, these are things like what's the carrier frequency that I need to go to in the next stage, or that I'm coming from in the previous stage, a pilot signal to synchronize everybody along the path. So each of these tuner circuits is is flowing at exactly some rational multiple of the network clock that's being used. We get to the other side of the link here, and we basically reverse those operations. We take those bursts, we slow them back down, we put them out to digital to analog converter, and then we have an RF tuner circuit that takes them to the proper carrier frequency and send them over the wireless path. And similarly, in the upstream direction or uplink direction, we reverse all of that. There's no control channel anymore, and just the wireless spectrum that's passing in the system. So you might ask, okay, how well does this work if I have a wireless system and I have copper cables? Here's an example. If you had Cat5e copper and you use basically one or two of the pairs in the Cat5e. We didn't show using all four of them here. This is actually a company I mentioned earlier, PhiTunes, that has done this work. It shows you what the throughput is versus the cable length. And as you can see, there's several hundred megabits per second out to a few hundred meters using the Cat5e type wires that you might expect to see, often twisted pairs. Telephone wires also have a similar gauge to Cat5 signals. And then coaxial cable is a little better copper transmission medium. And you can see the data rates here, over a gigabit per second out to a few hundred meters with the system. So it works reasonably well with 100 megahertz wide bandwidth signal, which is one of the wider bandwidths that you do see in the new 5G standards. So there's no need for the new cell site as long as you're within a kilometer to several hundred meters, and that's pretty substantial, especially at the frequencies that are contemplated for use, millimeter wave in particular, for 5G. And I didn't show a fiber plot here because essentially there's very little distortion on the fiber. So the results are better, and you can go a longer distance on fiber as well for this. So let me go back to those 10x improvements that we started our discussion with. The first is the cost reduction. So let's talk about that a little bit more. If you look at the needs of these tuner circuits, basically what happens is you will need a 12-bit precision A to D converter, D to A converter. I've added in here, I presume the fiber was used, an optical to electrical interface. The sampling rate is 1 gigahertz. And if you look at that type of device today, I went to a couple of experts. One's a former student, but he's actually the CEO of China's largest tuner company, and he estimated that at about 36 cents in volume, millions or more of chips being sold for the packaged device. And then one of my colleagues at Stanford also knows this area well. He had it at 25 cents in 7 nanometer CMOS technology, a little bit better technology. But you can see this is a very low price. If you add a small amount of microprocessor and memory to this, it's less than 1 millimeter squared to do this buffering you're talking about. That's about 10 cents per chip. And the total chip average sale price, ASP, is about 50 cents. If you looked at a little box for one of these tuners, the bill of materials, a BOM, the box would be about $2 sale price. So if you look at femtocells or routers or access points today, those are 60 to 70 dollars each, even in large volumes. So this is really a 10x savings here because it's a much smaller functionality by using the TransLink convergence. So essentially one form of cost reduction. Another independent form of cost reduction is just basically not having to build all the cell sites. What you use instead, and so you go to many smaller cell sites, but you use the wires to get out there, use the TransLink convergence, and so you really don't have to build as many cell sites to support the 5G interest. So if it's a fiber system, you're going to send the IQ samples non-coherently in separate bursts, but not as bits on the fiber. for the system, and use the existing silence gaps or some of the slots in the fiber to transport those bursts of samples. If it's coherent, you can just directly take it to the coherent systems carrier or wavelength, if you will, with split 7.2, and you can get many users bursted onto a single wavelength in both directions using any gaps in protocols or slots that are allocated in coherent fiber systems that are occurring so increasingly in the field. So you can use a separate wavelength also if you want. You don't have to do that. And the fiber can support the several tens of kilometers lengths. I put a square root on it basically because if you square that for the r squared in the density of a sphere, density of a circle, if you're looking at the density of devices, you're going to get 10x fewer cells required if you can get 10 kilometers or so on a fiber as opposed to having to move a lot of cell sites out. So it expands basically your ability to deploy. As I mentioned, existing copper can handle about 1 kilometer or so the square root of 10 kilometers, but still a substantial density improvement. So you get two forms of cost reduction. Those kind of tuner circuits, and then the need for less infrastructure investment to support. On the actual data rates and power, the user advantage is basically the ratio of the radius. If you look at a 5G radius versus the translink convergence radius, if the 5G was 200 meters and the translink convergence TLC there is 20 meters, then you get 10 squared or 100 times as many users that you can support in a unit of area, just simply because you have these smaller, lower power cells and you're getting to all of them. Now that may require a little bit more interference management. If you actually look at the path loss on that and you use 4 or even 5 for the path loss coefficient, enormous improvement there, 10 to the 4th. So a factor of 10,000. Now you might have 100 times as many antennas, but still 100 times your advantage in terms of power to do that. And you get cheaper antennas and you're still getting better spatial resolution because you've essentially used the wires as very narrow beams, if you will, and getting closer to the end devices. So it's a much higher use of all the available resources. It also reduces the uplink user element power, namely the battery in your cell phone, if you will, because it doesn't have to go as far. And so the transmit power out of your cell phone up to the system can be a lot less than it would otherwise need to be if it was going to a cell tower. So essentially what we've created is a kind of a massive hybrid distributed antenna system with many, many more cheap antennas. But it leverages the existing front haul split 7.2 and is compatible with all the 3GG things. So it's not an independent new system that's trying to be deployed as a DAS. It does provide an extra security layer. It's kind of a simple security concept. But if you look, and this is particularly true for enterprise uses where you're trying to use either 5G or Wi-Fi inside a building, what happens is you want to go to many places, then the signals are out there where they're more visible to hackers. If you use the wires and have a very low power signal, obviously it's not as easy to get access to all those signals. So a few more thoughts here as I get close to the end of the talk. If we are to start using artificially intelligent allocation of spectrum, increasingly dynamic allocation of spectrum at the data edge, so this is where the split 7.2 is occurring. This is very compatible with that, allows those spectrum allocation decisions to be made then with full knowledge of all of the subtended translink convergence underneath it. So you get an optimized use of space and time with it. And I would as long as we're doing that, if we take this and we maybe allow a little more cost where we were putting a tuner earlier, can we put a reflective intelligent surface like capability there? If you know about RISs, this is essentially what they do, is they're kind of creating a phase change and maybe an amplification at the RIS of a signal. It's very much like what we're talking about with the tuner circuits here. Put a little more capability and allow that to happen in those devices. Now we can begin to play with the spatial streams for the ultimate wireless link at the end of the system, and put in a little more processing to do that at each of these places. That'll increase the cost a little bit, but it certainly would increase the sophistication of the system and allow it to be managed still in software at the edge. So here's the full system doing that. Maybe a little bit of a complex diagram here, but the idea is having many of these base stations in software or access points in software, switching the signals around to different wireline paths. We might have a number of spatial streams on each of those paths. We have all the intermittent frequency devices connected to different wireline links, and then being sent out to wireless. And if we put that RIS type capability in the different places, particularly IF and the RF here, you could have a cloud managed system that's really fully optimizing. And in fact, a second invited paper I mentioned earlier is this one here from a couple of years ago as well. I'll call that ergodic spectrum management. That's a way of actually doing this. So it completely supports the cell-free concepts that allow a full virtualization at the data center, and we don't really have all the little cells. It all becomes kind of a software concept. So the wireless tradition so far has always been to add more time, frequency, and space. That's harder and harder to do. Even if we add a lot more antennas, go to thousands of antennas. Some of the work from TII in particular from group there, I quote at the bottom, has looked into the effective degrees of freedom, which is always less than the number of transmit antennas. The number of receive antennas are particularly important. The rank of the channel, and what the simple graph shows is that even though there's lots of antennas in the system, what's happening is you're saturating. There's only so much rank in the channel. It's not rich scattering enough. And so there are limitations even to space and antennas. And of course, there are always limitations to spectrum. So this is a concept here that we're looking at that basically gives us another shot at it without having to add more spectrum or more antennas, the translink convergence. Just a brief comment on precoders. If you really want to go and use maximum signal processing at the mobile edge, we can add nonlinear precoders to the linear precoders that are already in use. You can do that. There's a postcoder in the uplink direction. These are matrix multiplies. This is the 16 to 17 gigabits per second of control channel that we talked about earlier. That would only get larger. We went to better precoder techniques, so that would become more profound. And without going into all the details here, there's a solution for this. I'm going to basically say that when you do these nonlinear precoders, I should mention, you get into what's called non-orthogonal multiple access, which can give you a much higher sum rate over a large number of users. It's particularly important when the number of users exceeds the number of antennas or the number of effective degrees of freedom in the system. And you can see here in just a simple example with a couple of antennas and 3 users, and there's a band pass, a low pass, and a high pass in there. In the channel, you get double the data rate already from going to these nonlinear precoders on the sum rate. And of course, you got more users sharing it, you can get a rapid degradation. But if you can use these precoders, you can improve the system. So let's go back to our diagram again. Instead of sending that 17 gigabits per second, what I'm going to suggest is a couple of changes. First is the way they compute it today is not the best use of the link overhead capacity. It could do like the DSL systems do, the vector DSL systems. They actually send the error signal back. They don't try to do the computation locally. You can do that at regular intervals on a signal you know. And the translink convergence has this little control channel. And basically, you can put those error signals as sample values in the control channel and essentially get them for free. So you avoid 17 gigabits per second of overhead in transporting the precoder coefficients back and forth. And you can use the top end best techniques for precoder calculation and distribution as well. So then the translink convergence opportunity, we can leverage the ORAN virtualization more fully. We get the 10x improvements in cost, power, data rates, coverage, so forth. It simplifies 6th generation PHY, moves the processing to software and compatible with that split, where we try to do all the computation at the mobile edge or at the network edge. And you don't have to move all the signal processing back to the radio unit, which is some of the proposed changes to avoid that 17 gigabit per second problem that we were talking about earlier on the precoders being computed in a different place than where they're used. So with that, I thank you very much. And I've been talking about 45 minutes or so here, so I'll turn it over to everyone for questions.
Thank you very much, Professor John Cioffi, for this very interesting talk. Now the section is open for questions. So I encourage everybody, if you have any question, please feel free to write in the chat box. Okay, while you're starting, people typing the question. Okay, I have actually this is a very interesting topic which considering this kind of convergence, translink convergence, right? Considering a mixed channels. We have wireline and wireless channels, and have a kind of cascade channels followed by RAI and wireless. And yes, so you show that is much cheaper than the previous existing solutions. But another idea that came to my mind was related to free space optical wireless. Usually used for the last mile connection. In free space optical wireless is also a very cost-effective way to provide high bandwidth links in short distance. So what do you think? Could you please comment on that?
Well, I hadn't thought of that as one of the links for this, to be honest, Daniel, but that is a decent idea. Wherever you have a carrier system as an intermediate link, if you will, you could essentially the IF would be the free space optic channel, but you could send the samples and bursts across such a channel as well. The free space optics has had multiple opportunities, I think, over the last few decades. It's something that hasn't quite had its time come yet because of some of the issues related to the rain or atmospheric absorption and so forth. But certainly the concept here should work with any carrier system. You just have to have an IF frequency that's pertinent for that carrier system. So it's not like radio over fiber where you just have you just take the whole wireless signal and transport it on fiber as is, because there's a wide bandwidth on the fiber. In this case, it's taking advantage of the computation at the edge and the 7.2 in a little bit different way, but you could use it with virtually any type of system like that. But I hadn't given much thought prior to your question about the free space optics potential.
Okay. Any questions from the attendees? Okay, another question regarding the native AI concept, which is, I mean, a very hot research topic and expected for 6G. How the native AI control, for example, can be activated today using the existing Open Run architectures? Is it possible?
Well, that's a question. There's a lot of different concepts, I think, on the AI. So I'm not sure exactly which one, but I think what you're referring to is native AI being where essentially the functionality that would be a transceiver, like a receiver, is totally done in AI and learned from the system rather than using maybe the architectures and systems that we know. There are certainly many of the chip companies are doing that type of thing where they try to use the AI. What I've seen is to try to use the AI to reduce the power consumption of the chip, especially if it's one that's going in a cell device. So they're trying to use the cheaper receiver that doesn't take as much signal processing or power whenever the channel's good. And when the channel's not so good, they try to learn that. So they do a feature extraction, which is not fully native AI, but okay, it's an easy channel. I'm going to use a linear system and not worry about it too much, and I won't use too much power for that. Or it's a really difficult system, and I'm going to have to throw everything I have at it, and do iterative maximum likelihood like decoding, except that's being done in the message passing and algorithm is being done in a learned fashion in a neural net, like a recurrent neural net, as opposed to the typical iterative decoding type structures that you see. And that does seem to have some merit if it's done well. It comes down to the training and how do you do that? And because you're always trying to project with these systems what's going to be the correct architecture based on everything you've seen so far. So I think it's probably a step in the right direction for wireless, and many of the groups are doing it. And they avoid the whole thing about having to be able to know what the probability density of the fading is, if it's Rayleigh or Nakagami or something. All of those assumptions are almost never true, right? So they're learning it as they go from the environment with the AI. So that I think there's some merit to that as well.
I think this is some appropriate actions are being, started for the next generation Open Run, right?
Yes.
Okay.
I think it's already finding its way into the chip. Some of the groups that I've talked to that are, the experts in the chip design areas of the major semiconductor suppliers for this, they seem to already be doing that. They're well on their way to it.
Yes, exactly. Okay, during your presentation, one of the slides you mentioned reflective intelligent surface. It can be act as a RF unit, right? So do you have in working study, considering intelligent surface in the
No, not in that. I was drawing a higher level analogy to it. We don't call it the IRS so often. Sometimes they do outside the US because the name of the tax authority in the United States is IRS, Internal Revenue Service. So nobody likes the tax man, right? So we call it the RIS instead, the Reflective Intelligence Service, to avoid that analogy. But they basically how they operate. There's a couple of models you can do for. One is just like a phase change, and they absorb the energy from the signals themselves and then use that to do some phase changing from the input to the antennas to the output. So that's a little bit more than what I was talking about with the tuner circuits. But if you get a little more sophisticated, you can have kind of a unitary matrix transform for this RIS type of thing. And those, of course, improve the ability to form the beams and enrich the environment with more paths, so that you have a higher rank and you take better advantage of the MIMO. What I'm saying is that same basic functionality could be added to these tuner circuits in a very similar way. Okay, you have to kind of learn the channel on both sides, but you can change the gains and the phase in,
Yes.
in a similar way. And it's basically doing the same thing that the IRS is, but it's doing it, between the links at the junction.
Yes, exactly as a relay.
Yeah.
Right? Okay. Okay, any questions from the attendees? Okay, now if you don't have questions, okay, maybe just to conclude the seminar on time, I think we are going to the end of the seminar. Actually, it's almost 10. So I'd like to thank you once again, Professor John Cioffi, for your time and availability to deliver the talk. I know it's in USA is a little bit late. Thank you once again. And as usual, the seminar has been recorded, so I please disseminate this talk among your collaborators and research groups, colleagues. It will be available very soon at the TII YouTube channel. Okay, so thank you, everybody. Once again, Professor John Cioffi, thank you so much.
All right, well, thank you. And anyone who has questions, especially if they're tape delayed, I know it's like very early in the morning in like 6 a.m. or something in Europe, or if you may have people viewing on a delayed basis, they're welcome to send me an email and ask me questions that way as well.
Thank you. Thank you very much. And see everybody in our next telecom seminar. Thank you very much.